Hi, my name is Charlie. I'm with ZeroSquared.io. Today I'm going to do a walkthrough tutorial of how to program your Digilent Arty A7-35 board with the ARM Cortex-M3 DesignStart example design. This is the Arty A7-35. There are files in the ARM Cortex-M3 archive for the A7-100 as well, its big brother, so you might be able to use these instructions for that board as well. So our goals for this tutorial are to test out this entire flow, and there's sort of four parts of that. So our first goal is to test out the physical connection to the Arty board from the PC and be able to just use the Xilinx tools to take a default bitstream file and program it into the board and test that that flow works. Then we will set up the ARM Cortex-M3 directory and use the Xilinx tools to compile their code into a new bitstream file. We'll test out the ARM Kyle tool flow, verify that we can compile the Cortex-M3 example firmware, and then we will test that we can take our compiled firmware, merge it into our generated bitstream, and load that all successfully onto the Arty board. So those are our four goals. The prerequisite, obviously, is you will need the Xilinx Vivado tools. For the purposes of this tutorial, I'm using 2019.1. The ARM Cortex-M3 documentation and tutorials all use Vivado 2018, and so 2019.1 is the last version where the UI is consistent with all the instructions. After 2019.1, they start changing the UI to move away from Vivado SDK and move towards Vitis. And I may do an updated documentation and video later on when I get that flow consistently working. So for Vivado, if you haven't already, you will need to go to Hardware Development, Vivado Design Suite, download Vivado, go to the Vivado archive, 2019.1. You can ignore the updates and go down to the Webpack, the Windows self-extracting web installer. Obviously, this tutorial is for the Windows version. And so you will need to install that. In order to do that, you will have to create a Xilinx account and give them your address and go through the verification process for export controls, but that's generally not too painful. So once you have done that and have Vivado installed, we can move on and download our other necessary files. I already have them in this directory here in the middle, but you will want to download the Digilent board files. Just paste this link into your web browser and it should download it and should show up as this Vivado boards master.zip archive. And you can just extract that here, and you will need to go in to the new board files and copy all of these into your Xilinx Vivado install directory. 2019.1, data, boards, board files. So you will just copy all of these into this directory. I've already done that, so I'm not going to do it again. So once you have all your board files installed, I recommend creating on your root directory just like a C:/FPGA directory to put all this stuff in. It just makes it easier. So once you've done with that, you will want to go to the ARM DesignStart website and download the M3 IP. You'll want the DesignStart FPGA, Cortex-M3 for Xilinx, and at this point you will also have to create an account with ARM and give them your information and go through their approval process. Once you've done that and logged in, you should see this Cortex-M3 DesignStart download page. You don't want the DesignStart eval, you want the FPGA Xilinx edition. And so once you click on this download now, it should download this AT426 archive. I recommend adding a prefix to that just so you know what it is later. And you can go ahead and extract that here. And this becomes your sort of your main working directory. and I recommend go ahead and renaming that to ARM Cortex-M3 2019.1 in case you use another version of Vivado or have multiple copies of this thing. We can go ahead and delete the boards directory. And so now you can delete download the Micron flash memory model. Go ahead and paste that link into your browser, and it should download this N25Q128 archive. You can extract that here, and you will need to rename this. This was part of the documentation instructions, so it becomes part of the path later on. So you can take this directory and we'll move it down into the ARM Cortex-M3, put it in the test bench directory, and then we will need to copy a file out of it, the sim sftp.vmf file, back up to the test bench directory. So that should take care of the Micron flash memory model. Then you'll need to download the Cypress flash memory model. That shows up as a number.zip file. Your number may be different, but you can go ahead and extract that here, and you get an executable installer. So point that as well to your C FPGA ARM Cortex hardware test bench directory as well, and extract everything there. And if you go in here, go to hardware M3 test bench, you should see this S25FL128 directory. So if you see that, then everything should be good. We can delete the installer. I recommend at this point backing all of this up to some other location in case you need to redo steps later or redo these instructions for a different version. So at this point, we should be good and ready to fire up Vivado and give it a shot. So now we will go ahead and run Vivado 2019.1. It might take a minute. Throughout the video, if things take a while, I might cut pieces. Once you load Vivado, you will need to run a few commands in the tickle window to tell it where to find your board files, and then we will change into our Cortex-M3 working directory. I've had this problem before. And we're going to go ahead and create a drive letter, a v:" drive letter, just to simplify things. That points to your Cortex-M3 working directory, so you should see that show up. So now that we have everything set up, you should go ahead and plug in your Digilant board to your PC, and go ahead. We're going to open our project in the V hardware M3 for Arty A7 directory, this M3 for Arty A7.xpr file. Hopefully you shouldn't see any warnings or errors during this flow, and so it looks good. So just to test out that we can load the default bitstream file, we will go to the hardware manager and open our target, do AutoConnect. You should see your board show up. It should be able to identify what it is, XE7A35T. And so we will go ahead and program the device and select as a bitstream file this V hardware M3 for Arty A7 reference.bitstream. And we can go ahead and program that into our device. And it looks done. And once it's done, you should be able to flip the switches and push the buttons and see the LEDs light up. And once you look at the block diagram, you can see that the switches and the LEDs are interrupt driven. So if you flip a switch and the LED turns on, then you know that you successfully triggered an interrupt and the processor core handled that interrupt and set your LED, and so you know that it's up and running software. So now we've tested out the first part of our flow. So now we will move down to the Xilinx synthesis flow part of the document. So we can go ahead and open our block design, and you can see what we're actually dealing with here. Once that's up, you can see our block diagram. This is the ARM M3, the Cortex-M3 core, and your AXI interconnects. These are all your AXI peripherals over here, and you can see that each one of these peripherals has an interrupt that comes back around to the interrupt mux and feeds back into the Cortex. And here's your clocks and resets. And so you can drill down into any one of these blocks and see what it is we're actually implementing. And over here are the inputs and outputs for the switches and the LEDs. So we're just going to walk our way down the left side of the screen and synthesize everything. So we can just run synthesis. And that will take about 15 minutes, so I will cut here. You can watch the log, though, and see when the RTL elaboration synthesis stage is done. All right, and so when that is done, you should see this window pop up here, and we're just going to run the implementation flow. You just pick the default options, and you can switch over to the implementation log and watch that process. Okay, so that took about 5 minutes, and then we're just going to go ahead and generate our bit stream. That should happen relatively quickly. And so once that's done, we're just going to open the hardware manager. And again, make sure your board is connected. We're just going to program the device, but this time we're going to use the bitstream file that we created, which is under the runs directory, implementation 1, this A7 wrapper.bit bitstream. So we can go ahead and select that one, and it should program the board. Any LEDs you had set before should reset, and like before, you should be able to see your buttons and switches setting LEDs, which means that your processor is up and functional and running code. So now we have the FPGA synthesis process and programming process done. So we're going to move on to the Keel software flow. So you will need to go to keel.com and download the MDK microcontroller developer kit and install that. So we will go back to Vivado, open your implemented design. It might take a second on your end. And every time you generate a new bitstream file, you will need to run these 2 tickle commands in order to update your MMI file with the bitstream configuration. And then we need to export our hardware design to the software side of things so that then the Keel tools can compile the software for the correct memory configuration. So you want to set that to v:\software. There's no need to include the bitstream. And yes, you will want to overwrite whatever it finds at that location. So now we can just run file launch SDK. Make sure this is set to v:\software and v:\software SDK workspace here. And hit OK, and that should automatically load the Vivado SDK tools, or the Xilinx SDK tools. And once that is loaded, we need to do some minor configuration. Go to Xilinx repositories and make sure that this Vivado ARM software repository directory is here. Just add new to select that. I've done that already. And then once that is done, we will need to create a new board support package. So you can just pick all the default values from this screen and hit OK. And on this screen, you want to change the OS version to 6.7. Apparently 7.0 isn't supported. The instructions tell you to go to standalone here and make sure that standard in and standard out are set to AXI UART Lite 0, which they are, but take note of that because it's actually lying to you. So we will hit OK. It should generate the board support package for us. And we will go to, I'll show you, we'll go to V drive, software, M3 for Arty A7, SDK workspace, the standalone BSP, the board support package we just generated, Cortex-M3 include, we want x parameters.h. I'm going to go ahead and open that in Visual Studio Code. And what you're looking for here are two lines that include standard in base address and standard out base address. And you're actually not going to find those because, as I mentioned, the tool was lying to you about that being included. So we're just going to fix that real quick. So we're just going to close the system MSS and reopen it from over here. And now you will see the 6.7. So you go to modify this BSP's settings, and now go to standalone, and you'll see that it doesn't in fact have that setting. So you'll need to change these to AXI UART Lite 0 and hit OK. And now when you go back to code, you should see your standard in base address and standard out base address populated. If you don't have those, then once you get through the entire flow, the FPGA, the Arty board will be unresponsive. So now that we're done with that, everything should be loaded. So we can just go, oh, we have to copy a couple of files first. So you have to go to Vivado, ARM software repository, Cortex, BSP, standalone 6.7, source ARM, Cortex-M3, ARM-CC, and you will need to grab ARM rvct.c and rvct.h and copy those to V software, M3 for Arty A7, SDK workspace, standalone, BSP0, Cortex-M3 include. And we'll just copy those into there. Right, we need to go to V software, M3 for Arty A7, build keel, and double click on this UV project file. And that will go ahead and load the keel utility for us. Now from here, everything should be set, and we should just be able to go to Project, Rebuild All Target Files. And that should just take a second, and we should be done. So that should have generated our memory configuration file with the firmware in it. So to merge that into the bit stream, so we'll open a command window. We can close these now. We'll go to V, go to hardware, M3 for Arty, M3 for Arty A7, and there's a script in here called makeprogfiles.bat. So you will run that, and that runs another instance of Vivado in the background and updates the copy of the BRAM, which contains your compiled Cortex application. That should just take a minute. So when that's done, we can go back to Vivado, open up the hardware manager, program our device, and this time we want to grab M3 for Arty A7, M3 for Arty A7, M3 for Arty A7.bit. Program that file. So when that's done, again, you should be able to flip your switches and push your buttons and see that your processor is in fact running code and being responsive. So that is that. We've tested out our hardware connections. We've tested out the M3 Cortex synthesis flow. We've tested out the software compile flow, and that we can merge everything back into our bitstream and program everything. You can also load up PuTTY and connect to the board, and you should be able to see the text output that the board produces, and see it responsive if you hit the reset button. So in the next tutorial, I plan to cover how to actually add your own ARM AXI slave to the design through the block design editor, and then how to create some basic software to exercise your peripheral and output data to the screen. So that is it. Thank you very much, and take care of yourself.